Hello, everybody. Let's do something that I think is maybe review, which is how can we set up an equation with an unknown transformation that will force a curve through a particular point. So let's start with this. This looks like x cubed, could what plausibly be. And let's say we want it to go through a point like, I don't know, like 1 comma root 11. So up here. So one thing that we could do is we could imagine vertically shifting this just the right amount so that it goes through that point. And we don't know how far that's going to be, but we can imagine sketching a picture of it. So something like this. So how would we set that up? Well, we'll start with the equation we know, and let's have some vertical shift amount on the outside. So let's pause for a second. How do we know if a transformation is a vertical shift or horizontal shift? So if you imagine plugging in the value 1 in the original curve, or let's do a different value like 2. So if I plug in 2 in the original curve, plug in 2 as the x value. As soon as you cube it, this term right here, once you've evaluated it, has become the y value. So if you imagine what this is doing, if you were to evaluate it step by step, is you plug in the 2, you evaluate it, this is the old y value, and now you're adding a fixed amount to the old y value, no matter what the y value was. So another way of thinking about this is we're adding on the outside of the function, so that's adding the same amount to all the y values, which is why it's a vertical transformation. Okay, so how can we figure out which transformation is it? Like, what is the value of k that makes it go through that point? General mathematical strategy is plug in what you know and solve for what you don't know. So let's plug in the x and y coordinates for the point that we want to be true that it satisfies this equation. So there it is. We plugged in root 11 for y, 1 for x. We solve for k. So k is root 11 minus 1. This is a perfectly wonderful number. There's no reason to try and do anything other than that. And so then our final equation, we could write somewhere. Let's write it up here. So y equals x cubed plus root 11 minus 1. And this is the new equation. Okay, so let's do it a different way. Same point, 1 comma 11, root 11. But instead of shifting it, what if we were going to vertically scale it? So something like this. Same deal. So write your original equation, x cubed, but this time let's add an unknown vertical scale factor, and then plug in what you know to solve for what you don't know. So this is times 1 cubed is just 1. So we've got k is root 11, and so a different equation that goes through this point would be root 11 x cubed. Okay, so I'm going to set this up, and I'm going to let you try and think about it for a minute. So you may or may not know what this curve is. If you don't know which one it is, you will very soon. This is a logarithmic curve. And you can't tell what base it is here, but let's pretend that it's base 3. So let's pretend this is y equals log base 3 of x. So why don't you go ahead and set up a vertical translation to take it through this point, set up a vertical scale, and then I'll show you another one. So imagine what would you have to do to this equation to add those things. Okay, fair warning, here we go. So even though it's an unfamiliar function, that doesn't mean that you can't use the transformation knowledge you know. And that's like going to be an important piece of getting better at math, is getting comfortable working with functions that maybe you've never worked with before, but that you know that the same transformation rules should apply to. So I'm adding a constant on the outside. Here's a vertical scale. Let's do the same thing. Let's plug in what we know, solve for what we don't know. So I plugged in 4 and 2 as the y and x values. And I went ahead and I isolated k. And again, maybe you're not used to looking at numbers like log base 3 of 2 and feeling like that is a perfectly respectable number that could count as a solution. But it is. You know, like you've been working with square root 2 for a while. You don't feel the need to do anything else with square root 2. You recognize that that's just a number. Same thing here. Log base 3 of 2, it's just a number. It's the power of 3 that will give you 2. So you can just keep it like this, nothing wrong with that, but don't put a box around the k value, because the goal wasn't so much to solve for k as to come up with the original equation. So let's go ahead and rewrite the original equation. There we go. Let's do one more. So I'll plug in what I know, solve for k. So there it is. You see I've plugged in 4 and 2. I'll divide by this whole thing, which is just a number, You know, if this had said 5k, you would have divided by 5. And so now we know what k is. Plug it back in up here. We're done. Okay, I want to point out one last thing. So if you happen to know that this is the point 1, 0 on the curve, and you want to translate this function so that it ends up on that point, possibly an easy thing to do would be to realize that you could translate this curve 1 to the right and 4 up, so that this point ends up here. And so in that case, let's rewrite our original function. So log base 3 of x. So if I'm translating 1 to the right, that would look like x minus 1. And then if I'm translating up by 4, that would look like adding on the outside. Okay, so I'm assuming it's review why the horizontal transformation looks like this. I'm not going to review it in this video. That was sort of last year's stuff. But if you don't know, I would definitely urge you to seek out a video so that you can understand why that's true. But anyway, so that's my whole point is you can use these techniques flexibly. You don't always have to plug in what you know and solve for what you don't know. You could also realize that you could shift one point to be somewhere else in the plane. Now let's sketch it. So this would end up looking something like this. It wouldn't quite go through this point. Something like that.